Something very nice about derivatives is that we can use the derivative to obtain information about our original function. And this is precisely what we're going to do in this video. We're going to learn some ways that we can obtain information from the derivative to conclude that, for example, a function is increasing, decreasing, or constant in a given interval. So here we'll see this graph here. We have between a and b, our function was increasing, between b and c, the function is decreasing, between c and d is again increasing. And if we take a look at the tangent lines, we see that between a and b, the tangent lines have positive slopes. The slope of the tangent line is positive. Then between b and c, the slope of the tangent line becomes negative. And again, between c and d, the slopes of the tangent lines are again positive. So it gives an idea that if my function is increasing and differentiable, then it looks here that the slopes of the tangent lines are positive. So now, if I know that my function is differentiable and I can see that the slopes of the tangent lines are positive, can I conclude that my function is increasing? And also, if I know that the slopes of my tangent lines in a given interval are all negative, can I conclude that the function is decreasing over there? The answer is going to be yes, and that is what we're going to do in this video. And our tool to prove this is going to be the mean value theorem. So this theorem tells me that if f is differentiable on an open interval ab, and I know that the derivative is positive for all points x in the interval ab, then f is increasing. And if I know that the derivative is negative for all points x in the interval ab, then my function f is decreasing. And we're going to prove one, and the other one I'll leave it for you as an exercise. It's very, very similar. So what we want to prove? Well, we want to start with 2 points, x1 and x2, that are in the interval ab, and we're going to assume that x1 is less than x2. And since we want to prove that my function is increasing, we need to conclude that f of x1 is less than f of x2. Okay. Since f is differentiable in the open interval ab, we know that f is differentiable on the open interval x1, x2. So it's a smaller interval inside ab. And the function is going to be continuous on the closed interval x1, x2, because my function is differentiable in the open interval ab, so and x1, x2 is strictly inside that interval. So then the closed interval x1, x2 is entirely contained inside my interval a, b. So I can say indeed that my function is continuous on the closed interval. Perfect. So my function is differentiable on the open interval. It is continuous on the closed interval. So I can apply the mean value theorem here to find a point C between x1 and x2, such that f prime of c is equal to f of x2 minus f of x1 over x2 minus x1. Okay, but now we know that the derivative is positive for all x in the interval ab. So that tells me that f prime of c has to be positive. So this tells me then that f of x2 minus f of x1 over x2 minus x1 is positive. Okay, so if I know that this is positive, what can I say about f of x2 minus f of x1? Well, we know that x1 is less than x2. And because I know that, then I know that the denominator is positive. So the only way that my quotient is positive is that the numerator is positive. So then we have indeed that f of x2 has to be greater than f of x1, which is exactly what we wanted to prove. And as I said, I will leave it for you as an exercise to prove part 2 of this theorem. But I'm sure you can do it because the proof is very, very similar to this one. So, now that we have this, we know that if the derivative is positive for all points x in the interval ab, then my function is increasing. Now what happens if I want to know a bit more? So you see, the previous theorem is not telling us the complete story. For example, if I look at the function f(x) equals x squared, this is increasing on the interval closed at 0, so infinity includes 0. It's increasing starting from 0. But the previous theorem would only give us something about the open interval. Okay, we would like to extend this a bit more, so we can improve this by adding an extra condition, and is that if I know that my function is differentiable and has positive derivative for all points x in the open interval, but in addition to that, I also know that my function is continuous in the closed interval, then my function will increase in that closed interval. And if I know that my function has negative derivative for all points in the open interval AB, and I know my function is continuous on the closed interval AB, then I can guarantee that my function is decreasing on the closed interval. This is a quite useful extension of the theorem. I'm not going to prove it, but if you're curious, you can try to give it a go yourself. And then as an exercise, I'm going to give you this one. And it's that if I know that a function is such that f prime of x is equal to 0 for all x in the open interval AB, then f must be a constant function. So this theorem, what it does is it completes the proof of the fact that a function is constant if and only if the derivative is 0 at all points. So it's a nice exercise for you to complete. Try to prove both directions. First direction is that if I know that a function is constant, then the derivative is 0. That one you can prove using the definition of derivative. And then this one in the other direction, that if I know that a function has derivative equal to 0 for all points x in the open interval, then the function must be constant.